the last time we started introducing the idea of parallel transport, and the rough definition was it's a way of moving a vector so that the derivative of the vector doesn't change, or the vector doesn't change along the path. And then we went on and we defined a covariant derivative operator. And the way we defined it was with basically these 5 axioms of that it has to obey, and the fact that it is, if you apply it to a type KL tensor, it results in a type KL plus 1 tensor. And then we showed that there's always one that exists, which is your ordinary derivative. And then we went and said, well, what can we say about other derivative operators? In fact, if you have 2 derivative operators, how does their action on a tensor differ? And we had directly from the 4th axiom that the action on a 0, 0 tensor, namely as the action on a scalar, is exactly the same. And then we went on and we explored the action on a 0, 1 tensor of 2 different operators, and we showed that it depended only on the value of the 0, 1 tensor at a particular point. And as a result, it could actually be viewed as a linear map, which is a tensor itself. Okay, and so then we went on further, and we basically said that the difference between 2 derivative operators can be summarized in terms of a tensor field that we called C with 3 indexes, 1 up and 2 down, in the following way. Okay, and in doing so, we basically captured the fact that the difference between 2 distinct derivative operators are simply equals dependent on the value of basically the one form, the 0, 1 tensor at a particular point, where you can encompass all the changes, and this is basically, if we will see later, the changes in the actual basis vectors in terms of this tensor CAB. Okay, and we're going to learn a lot more about this tensor field CAB, and this is just the way that guarantees its existence. That's what we've basically proved, as well as helps you characterize the difference between 2 derivative operators. And then we said there's a property, a symmetry property on this tensor, and you saw that by looking at the special 0, 1 tensor, that's the gradient of an arbitrary function, okay? And by applying this property to 2 different derivative operators of this gradient of the arbitrary function, we basically have this expression, okay? Nabla AF, Nabla BF is not necessarily equal, is definitely, well, in most cases not equals to the different derivative operator. The only thing you can get from this is that because f is a scalar, you can switch these 2 around, and therefore this whole part is symmetric in A and B, and therefore C must also be symmetric in A and B. Okay, so that's one of the properties that we had, or sort of derived, is that this tensor has the property that CAB is equals to CBA. Okay, and now what we're going to do is this, basically explore the difference between the action of derivative operators on vector fields. Okay, so we've got 0, 1 tensors, which is basically the dual space of your vector field, and let's go back now and use the information to explore what it has, the impact it has on vector fields and on higher rank tensors. And so on vector fields, you can also show that rather than obeying this identity where you have the one derivative operator applied to WB is equals to the different one minus this tensor, the derivative operator's difference when it's applied to vector fields obeys this expression. So you, instead of having a minus over there and summing with C on the top there and the index below, you have this thing where you have C, B up at the top, which basically captures the fact that you have a vector field, and then A and then C at the bottom being contracted with T at the top. Okay? And so it uses the same tensor, and you can define the difference in the derivatives. It's just the way it's contracted is different. And the way you can see that is basically to compute the difference of the two operators applied to a contraction. Okay? And then use what you already know about this derivative operator. So if to get this thing, you basically compute this entity. You know that this contraction is basically a scalar. Okay? So that entity that you're applying it to is so WB times the vector sort of contracted with a vector TB, so it's effectively a dot product. That's equals to a function, which is a scalar function. Okay? And therefore, for this particular expression applied to a scalar function, the two operators must agree, because that's the definition of what your derivative operator is. So we have that this thing is equals to 0. And what we can now do, so we know it must evaluate it to 0, but we can equally take Leibniz and simply work out the use Leibniz's rule and work out the effect of this operator before we contract it. And the way we do that is simply say apply the operator to WB and contract that with TB, and then contract W lower B with the operator, or the difference in operators applied to the vector field TB. And if you do that, what you can do immediately is you know what this is because of your existence proof over there. So you can simply write down what this difference in operators are applied to WB, and that simply equals to CCAB contracted with WC. So there we have it. And notice what happens here with the C, right? You're applying it to WB, but then the WB gets taken up into the tensor, and you're actually contracting the C with one of the other components in the tensor. Okay, so this then is the expression for that, and then you're left with WB times this difference of operators applied to TB, which is what you actually want, and what you then do is you basically rename the contracting indexes in the first term. So what you can do is, because this contracting indexes, you're simply summing over it, you could say this is C alpha W or omega alpha, and you could rename B to be, say, beta. And in this case, what you're going to do is simply you're going to swap the index names on C and B. Okay? And you can then get this expression. And the reason for doing that is that you want a WB common to the thing, because that's the only thing that doesn't appear in there, and you're then going to make the argument that it's got to be true for any WB, therefore whatever WB is being contracted with must be 0. So you change the indexes, you then take WB out, okay, so this you can still do, and so you're left with a square bracket contracted with WB, and you know it's got to be 0. So what you have then is that this thing must hold for all one forms or cojudgant fields, WB or WA, whatever index you choose to use, and therefore this thing inside the bracket must be 0, and therefore you have this identity. Okay, so you once again have, and so you can now see how this expression arises that was given up here. It follows directly from this change in operators with this tensor C, which I haven't told you how to calculate this yet, simply coming in, and then when you apply the change in operators to a scalar function, which you know must agree, you eventually get out that the difference in operators applied to your vector has this expression. Questions here? Not yet. It's manipulating indexes. The moment you've got that the difference in operators applied to your one form, you get the vector fields rule out, and you get a whole bunch of, and you get basically the rule out for any tensor as well. Okay, very important. These two expressions are different. Okay, and know them carefully, right? This one, when you're applying it to a one form, the lower index, a 0, 1 tensor, you have the minus c a b omega c. If you're applying it to a vector, you have the plus, and the contraction is now with the upper vector index and the lower index in C, and the symmetry is still on the lower two indexes and not with the upper one. Okay, so then we can go on and we can work out the difference in two derivative operators. Basically show that for any tensor field, the only thing you know to work out the difference in the two derivatives operator is this tensor field C. So the method of doing it is very similar to what we did now. We defined it for the one forms, then from the one forms we got that it was defined for the vectors, and you could do a similar thing, and basically, by taking contractions, applying the derivative operator, using what you know of the thing that you've contracted with, you can eventually show that for any tensor T, Lk, if you apply the derivative operator to it, and you apply another derivative operator to the same tensor, these two are equal, provided you add something that looks like this. And so the rule is, you add for every single index, okay, in this upper tensor, right? For example, you pick one, say AI, you replace it with F, then you add C, F below, and then the index you replace, you put CI at the top there. Okay, so these are all the upper indexes, they behave like vectors, and all the lower indexes, like for example here, they behave like one forms. You basically, for every lower index, you pick your index and you've got a sum over all of them. You say call it F, you contract that with CF up here, and then you take the index you had and you place it over there, so that's your BI, and then you have C over there. Okay, and so once you have this thing, you can work out the difference between every single tensor field that you have, or the derivative operator applied to every single tensor field that you have. Okay, the converse, basically, if omega tilde C is a derivative operator and CAB is an arbitrary smooth tensor field, which is symmetric in its lower indexes, then nabla C defined by this equation above is also a derivative operator. Okay, so the first, it's true that if you have one derivative operator, any other derivative operator can be written in this form. And if you have a specific derivative operator and you have any field C, you can always, that is symmetric in these lower two indexes, you can always find another derivative operator that obeys that obeys the 5 axioms you had, and that if you use this rule. Okay, so we've been playing games with literally derivative operators, and we've shown that the difference between them is completely contained here. But to date, we haven't actually given you a way of finding, well, we've given you one specific way, which is the coordinate derivative operator, but we haven't actually worked on how to work out the C's, and we're going to do that now. Okay, important, these things, every statement I've made doesn't depend on a metric. Okay, when the metric comes, or when you have a manifold that has the derivative operators and a metric, then you can play many, many games. But the idea of a derivative operator in parallel transport does not require a metric. Okay, just another thing which is very useful actually when you start working these things out is to know how much work you got to do. And so in an n manifold or an n-dimensional manifold, the number of components that this thing has, right, is, if we didn't know it was symmetric, it would be n to the 3. Okay? But because we know it's symmetric, you have n ways of choosing C, n ways of choosing A, and then it's just the upper diagonal elements because it's symmetric, so it's n plus 1 over 2 ways of choosing B. Okay, so there are n squared times n plus 1 over 2 independent components of the C. So for example, if you have a 2-dimensional manifold, or what you're going to have is 6 of these elements that you have to work out. And it gets bigger the more you go up. Now, okay, this is the thing that most people know the C operator as. Okay, they call it the Christoffel symbols after the guy that got it or sort of understood it first. And very often we denote these by gammas. So what these Christoffel symbols are is, in the special case, with the one derivative operator we know so far how to compute easily. In other words, the case where you take the tensor and you just take the derivatives of the components of the tensor as expressed on the chart. So if you have that derivative operator, then the gammas associated with that derivative operator, okay, so this is the coordinate derivative operator, then the gammas associated with that, in other words, that connects any other derivative operator with that specific one, instead of C, we call them gamma, and we call them a coordinate system. So these, this tensor field C, in the special case where your one derivative operator is simply the coordinate derivative operator, we call them gammas, and those are often known as the coordinate system. And so now for the first time, we get a concrete way of actually computing a general derivative operator. You have this derivative operator A applied to T, just for example, the tensor field, that is the derivative of the components plus this gamma times this TC. Okay. And the thing is that this dA, as I said in the past, is associated with your coordinate system because it's just taking derivatives with respect to the coordinates. And if we know what these gammas are for that coordinate system, then we've basically defined our general derivative operator. Okay? If we change coordinates, the ordinary derivative operator, this thing is going to change to a new set of coordinates. So for example, if we go from Cartesian coordinates to polar coordinates, the thing with which you're taking derivatives with here would be dx dy dz, and here it would be dr d theta d phi. And what then happens is that for every one of these operators, you're going to have a new tensor gamma. So associated with this thing, if we're in flat, the gammas are just 0. If we are in polar coordinates, these gammas you can actually work out, and they're very closely related to how your unit vectors actually were changing. Okay. Another important thing, these gammas in the new coordinate system are not related to the gammas in the old ones by a tensor transformation law. In other words, you cannot just transform this tensor into that one by multiplying by components of the Jacobian. You just can't do that because this derivative operator is associated only with that, this tensor is associated with that derivative operator, and this tensor is associated only with this derivative operator. But what is true is that once you have that pair or that pair, they combine to make something that doesn't depend on your coordinates. Okay. So now that we have a little bit more machinery, let's go back to parallel transport. Okay, so parallel transport and its stricter sort of definition that we're going to use to calculate is, given a derivative operator and a curve C with tangent TA, a vector VA at each point on the curve is parallel transported along C if the derivative operator applied to VB dotted in with TA is 0. In other words, if the directional derivative associated with a tangent of the curve applied to the vector is 0, then you're parallel transporting. So that's our very clear definition of when a vector does not change. Okay, so we now are going to have, we want to now define parallel transport. So to parallel transport it, you want a curve, okay, on the manifold that we call C. Associated with the curve, you have tangents, okay? And so we say a vector, any vector VA is parallel transported, okay, if it obeys this equation. And I'll give you an example as well. If the directional derivative along the curve applied to VB is 0, then you're parallel transporting. So it is exactly that picture that we had in flat space. It's simply keeping the angle the same. Okay, and in the curved space, it's also keeping the angle the same. And this is just the formal way of writing it down, and we're actually going to see this eventually gives us the equations for working it out. Okay, so if that is true, that's the definition of parallel transport. Okay, and to express this in terms of a coordinate system, what we're going to do is simply write this down. So this thing becomes an equation. So it becomes TC, the derivative, the normal derivative operator applied to VB, plus, I'm just writing out the definition of this gradient, plus TC times the Christoffel symbols BCA VA. Okay, sure. Okay. And if you are working on a coordinate basis where T is a parameter along the curve, okay, so this T is now not the vector T. Okay. What you then can write it as is this T times dc VB, okay, is simply dv dt, okay, times T mu times gamma times V, gamma V contracted with, gamma V mu lambda contracted with V lambda. Okay, so this thing is exactly the same as saying ddt of V, okay, because ddt of your vector is simply the vector's derivative with the way the vector changes with respect to coordinates multiplied by the coordinates, how the coordinates change along the curve, which is just TC. Okay, and that then is your parallel transport for a vector. Your parallel transport for a tensor is also simply the same thing. Take the derivative, apply the derivative operator to the tensor, contract it with the tangent of the curve you're transporting it along, and that must be 0, then you've parallel transported your tensor. Okay, so for example, the parallel transport of a vector VA depends only on the values of VA on the curve. Okay, Okay, so to be able to do this, you don't necessarily have to have a vector field everywhere. You simply have to know the values of the components of VA on the curve to be able to parallel transport it. And what that means is that this equation is basically an ordinary differential equation. And that means that there, just from the ordinary differential equation theory, is that there's always a unique solution. So you can always parallel transport any vector because of basic ODE theory, right? And you're guaranteed at least a local solution. Okay, so if you start with an initial value of a vector, you can parallel transport it along any curve. And also the vector at the specific point where you start uniquely determines the vector along the curve. Okay, and that follows directly from what we know about ODEs, because you can actually write it this way, and these things we still have to compute for you in a way. Okay, so what that means is that parallel transport can be used to identify two tangent spaces. Okay, if you have it, remember up until this point we only had a tangent space at one manifold. We did everything just at that point, and then if you went to a different point, it was a completely different tangent space. Okay, what we can now do is we can start at point P, look at its basis vectors, and then transport those basis vectors using a curve from point P to point Q. Then they would have moved. Then we can work out the projection of the transported basis vectors at point Q, simply project them onto the tangent space at point Q, and so we can have a connection between the vectors at two different tangent spaces. Okay. And this is only, and once again, you can only do parallel transport if you have a derivative operator and you have a curve connecting the 2 points. Okay, so we still have our parallel transport equations. We have these gamma factors coming in, which we now basically are going to focus on a little bit more and start computing them. And I said that those things are basically keeping track of how the basis vectors change. And that's also, you can see, because to connect the two tangent spaces, you're basically going to parallel transport one vector from one tangent space to the other one. To be able to do that, it's simply how the components change multiplied by this tensor. So this is literally keeping track of how, when you go from one point to another one, your basis vectors are actually shifting. So that's the other place you can see that this thing is actually associated with how your basis vectors of your tangent spaces are changing. Okay, so just a name for this gamma or the C's we've worked with is we call it a connection. Okay, so the mathematical structure arising from a curve, from curve-dependent identification of the tangent spaces, okay, of different points. Okay, so now if you're given only a manifold with distinct derivative operators, if you're given only a manifold, many distinct derivative operators are possible, and none of them are naturally preferred above the others, okay? And that you could see because you had one coordinate derivative operator, you could get a nabla from it with these tensors, but you could just choose a different coordinate operator and make another thing. What does happen is if you have a metric, the moment you have a metric, this changes. So you can do parallel transport on a manifold, and you can have several derivative operators, but the moment you define a metric, you can no longer do that. You specify, the moment you have a metric, you specify the actual derivative operator that you're looking at. And the way you specify this is because a metric naturally defines an inner product. And remember, we use the inner product to be able to specify what these gamma things were when we changed them. So let's see how it happens and how, in fact, we compute these things if we have a metric. So what the metric does, it gives a natural condition to impose on parallel transport. Okay, so, and the way we see that is if you have two vectors, okay, their inner product is simply GAB, VA, and here's a mistake, it should be VB over there. Okay, so the inner product is GAB, VA, VB. Okay, and this thing should remain unchanged if we parallel transport, because this thing is just a scalar. Okay, so what we're basically going to require is that if we parallel transport this thing, okay, which is a scalar, that must be 0. Okay, and the way we then parallel transport it is simply to apply our parallel transport operator, in other words, the derivative along the curve of the scalar, and we say that must be 0. Okay, and so we say that basically we require this to be 0 if we parallel transport the vectors themselves. Okay, so what we're going to do is we're going to parallel transport vector B along the curve and parallel transport vector W along the curve, and then we are going to require that that the contraction of them doesn't change if we do that. And what that basically does, if we apply Leibniz's rule to this above condition that the contraction doesn't change, what we get is that we basically apply Leibniz, so it's the gradient operator applied to GBC dotted in with VB and WC, okay, plus GBC times the gradient operator or the parallel transport operator applied to VB, but we're assuming that that's 0. And similarly, when we apply the parallel transport operator to WC, we're also going to say that's 0 because we're assuming we're parallel transporting both VB and WB. Okay, so there I've just written it out. Okay, so this is simply Leibniz applied to this condition. And what that means is that only the first term remains. Okay, and so the moment we have a metric that gives us this inner product, which is just a scalar function, and we parallel transport that, we have this condition. And what that is that we want this condition to hold for all C, in other words, any single curve, therefore this tangent vector is arbitrary. Yeah?
Door just plus just underneath the Leibniz word, that term just underneath it. Must the VC be in front of the TA derivative in terms of A? The one just below it, that term?
This term.
Yeah.
So
must that VC be there, or should it be
V?
Yeah. WC, sorry. I'm saying
yes.
V, like Afrikaans V.
Yeah. So look, you're expanding this thing.
Yeah.
Okay, so you use Leibniz, so you first apply the derivative operator to GBC. Okay, so that's the first term.
Yeah.
And then you plus TA, you have the derivative operator applied to this VB.
Yeah.
Okay, so there's that term. And then you multiply it with WC.
Okay, so there's basically a bracket.
Yeah, so whenever you apply the derivative operator, it's only to the thing that follows it.
Okay.
Unless you've put this bracket in. Okay, there you're applying it to all three. If you have no bracket, you apply it just to the one that's immediately afterwards.
Okay, now then it's fine.
Okay. Okay, so this thing basically must hold for any curve and any vector. So basically you are free to choose TA, VB, and VW. And what we therefore have is that the gradient operator applied to the metric must be 0. Okay. And this is what chooses the gradient operator. So the fact that we require a dot product to be between vectors that are parallel transported to be the same regardless at this point or that point, okay, immediately leads to the fact that the gradient operator applied to the metric must be 0. Okay, so the metric is something, a tensor, that doesn't change for this particular derivative operator. And this thing now provides an additional condition that allows you to specify the unique derivative operator that doesn't change the metric, and therefore makes inner products at different points make sense. Okay, and so this condition then chooses which operator you have, which derivative operator you have. And for all practical purposes further on, we're going to work only with derivatives operators that are associated with a metric. The reason for doing it this way is so that you know exactly at which point your assumptions are being, or your specialization is being made. There are no assumptions being made. It's simply specializations of a manifold with a metric always has a unique derivative operator. Okay, and so if we have this derivative operator, we can now go and we can actually get this connection. In other words, those gamma things that connect the basis vectors at one point with the basis vectors at another one. Okay, so let's do this now. And here the actual computational techniques come in for actually computing these gammas. So if we say let GAB as a metric, okay, then there exists a unique derivative operator, which we call nabla A, that satisfies this condition that basically the metric, the derivative of the metric is 0, ensures that your inner product is conserved if you parallel transport vectors between 2 points, and it has another number of other consequences, because the moment you have this, you can actually go about and you can compute all those gammas that appear in that we've been speaking of earlier on, that constitute the connection. Okay, so the way we prove this is we say let nabla tilde be any derivative operator, okay, and an example would be just the ordinary derivative operator, which is the derivative with respect to the coordinates on the basically once you've used the chart to map to Rn. Okay, if you're given a chart, and remember we said that this derivative operator isn't a tensor, it changes depending on your coordinates. It's dependent on the coordinates. And the aim now is, if you're given this operator, is we want to solve for these CABs. And the moment we solve for these CABs, we've actually fully specified the new derivative operator that obeys this property. Okay, so the moment we have the CABs, we can have this new derivative operator determined in terms of the ordinary derivative operator. And the CABs also basically has the property that the gradient of A applied to GBC is equals to 0. Okay, so what we're going to do is we're going to show that these CABs have a unique solution, okay, and the way we find them is we basically start from the general equation for the action of this thing on a tensor, okay, and then we set it equals to 0. So we know that 0 is equals to the gradient or the derivative operator applied to the metric tensor in order to preserve our inner products. And what that means is we simply write out what this derivative operator is in terms of this other derivative operator. So we have that this thing is basically the other derivative operator applied to GBC minus, okay, both indexes are lower, so they behave like one forms. So it's minus C D AB times G. So you're contracting the D's, so whatever was there would be B over there. Sorry, and there's an extra minus here. Minus CD, okay, A, and then you are basically replacing the C, basically, you are contracting over D. Therefore, whatever was in D's place must go down there. So you have AC, G, BD. Okay. And what we can now do is we can actually go on and we can say we can lower, we can combine these things and we can actually show that C or CAB plus CBAC is equals to this operator applied to GBC. Okay, so how does that happen? Okay, firstly, we know that this thing must be 0. Okay, so if we can basically lower these guys, oh no, we can't lower these guys. Okay, how did I do this? Oh, okay, so this thing, if you multiply this tensor with your lower metric, you basically lower the top index. Okay, so you basically have, I just moved all these guys to the left hand side and I simply contracted C, D, A, B, okay, with this G, D, C, so that basically means that this D went down and it became a C, so that's that term. And this guy I also moved to that side because I'm contracting the C, D, AC with this metric, I take the D and I replaced it with a B, so the B went down. Okay, so we have this expression is that that operator applied to your metric. Then it can be true also if you change any of these indexes, right? So if you happen to switch A and B, they're just dummy indexes. You would also have to switch A and B over here and A and B over there, and this is the second result.
Sorry, can I just
yeah.
ask, in the top line where we have zeros equals to the operator A, G, B, C, they're the last term, there's 2 minuses, is that just...
That's a mistake, that minus should not be there. Yeah, sorry. I don't know how that crawled in. Okay, and then you can do the same thing, is you can switch, you're just changing the indexes. So you can basically, you have A, B, C here, you have switched A and B over there, and then over here you have basically switched C and B over there. And then what you do is if you add the first two and subtract the third one, you actually get an explicit expression for a C, okay. Okay, if you add, yeah, right. If you add the first two together and you subtract the third one, so what do you get there? And you use the fact that the C's are antisymmetric in the last 2 indexes. In other words, you can switch these A and B around, okay? So then you have 2 of these guys adding together, and then you can subtract, when you subtract the third one, those 2 cancel, and these 2 cancel, okay? Then what you get is simply 2 of these guys equals to this plus that minus that. Okay, and so what that means is that basically you can get an expression for these C's, B, A, D, in terms of this operator, which we can take to be just the ordinary derivative operator applied to the metric. Okay, and so what this is, if you're given the metric, what you can do is you work out the ordinary derivatives of the metric, of the indexes. You then get a giant combination and you work out the inverse of the metric, and then you can actually get every single one of these components simply by taking the derivatives of the metric. Okay, and so this thing then basically solves the fact that this thing is equals to 0 and it's unique. Okay, so this expression over here is important because you can actually use it to work out your connection. And that's when you're actually doing practical calculations, you're going to get your metric. You're going to work out the derivatives of the metric, work out the inverse of the metric, and then work out all these coefficients, which are then your connection for that metric. And these things then basically connect the tangent space at one point with the tangent space at another point. Okay, so now basically we have our metric determining the unique derivative operator. It's called the natural derivative operator if you're given the metric. And for this case, the Christoffel symbols are associated with the coordinate derivatives are basically this. Okay, so given the metric, you work out these partial derivatives with respect to the coordinates. You contract it or sum over C with the inverse metric times by half, and then you have all your Christoffel symbols, and then you can actually parallel transport any vector in that metric by writing down the equations earlier on, and I'll give you an example of that now. Okay, so you can compute those by taking partial derivatives. Let's have an example. Okay. So once again, we're going to go back to the parabolic coordinates because it's simply an example that is unusual. And we're going to have a flat Riemannian metric in 2 dimensions. In other words, our Cartesian coordinates are going to be this. And the components of the metric are 1, 1, and 0, 0. From this, you can immediately see if you take derivatives of this metric, you immediately get 0. Therefore, your connection of the Christoffel symbols vanish. Okay, so that's if your metric is just the ordinary one, if you're Cartesian coordinates. But suppose you want to parallel transport a vector along a parabola. You can then go on and you can change to your parabolic coordinates, which we did the last time. Okay, so then we had the 2 new coordinates, and we then worked out the inverse transformation, and we basically could work out that our transformed metric basically had the components G11 equals to the sum of the coordinates squared, which is equal to G22, and the off-diagonal elements were 0. Okay, so that's just some of the preparatory work we did the last time. So now we actually want to go on and we want to work out our connection for basically these metrics. And because we're working in 2 dimensions, let's see how much work we have to do. We have to work out the 6 independent components of the connection. And so these components are simply gamma 1, 1, gamma 1, 2, 2, gamma 1, 1, 2, but that's equals to 2, 3. Okay, because it's symmetric in the lower indexes. Gamma 2, 1, 1, gamma 2, 2, 2, and gamma 2, 1, 2. So I usually, just for my own sake, when I start, I write down all the potential Christoffel symbols I want to work out, and I make sure that the number adds up to the number of the dimension. Okay, so the connection associated with this derivative operator ddxa, okay, in this case where all the metric coefficients are constant, you basically have all the metric coefficients or all the partial derivatives of the metric vanishing. So all these guys for this metric are 0. Okay, so what we then have is our parallel transport equation for any vector, if we're working in Cartesian coordinates, is simply the tangent times, the tangent vector times d gamma, nu mu lambda times v lambda. So that's just the parallel transport equation written out. But because all these guys are 0, you have that the vector doesn't change as you parallel transport it, so your vector is basically constant. So that's basically restating the obvious for vectors in this Riemannian manifold, right? If you move it along any curve, the vector components are going to remain the same. Let's now see what happens when we work in a new coordinate system. Okay, so here it's the same manifold, okay, it's just different set of coordinates. But in the different coordinate system, the connection we can go about, and the connection is associated with a derivative operator, which is basically the coordinate derivative operator. So it's dd xc alpha. Okay, and so what we're first going to do is we are going to basically compute this connection. So the way I like to do it is I compute all the lower indexes like that, and then right at the end I simply multiply or contract this first index with a metric to raise it. Okay, so I basically want to compute all these combinations to actually get these coefficients. And so let's actually write it out. So you have gamma 111, that's simply a half ddxc1 g11, and that is equals to xc1. You're going to have gamma 222 is simply a half ddxc2 g2, and that's equals to xc2. I have no idea where the star comes from. Okay, that shouldn't be there. So gamma 122 is simply equals to minus a half, and I'm writing out this definition, putting in the specific indexes. So it's ddxc1 g22 plus ddxc2 g12 plus ddxc2 g12 because it's symmetric. Okay, and if you work that out, you know that these guys are 0, so it's just ddxc1 of g22, and so it is simply minus a half times 2 times xc1, so it's just minus xc1. Then you can do the same with gamma 112, it's just these derivatives, and that's simply xc2, and then gamma 211 is just, you do the same thing, minus xc2. Gamma 222 is xc2. Gamma 221 is xc1. Okay, and then to get these things that actually enter in the equations, I then go and raise the indexes of these gammas. And so I'm basically summing over delta. So what I then have is that gamma 1 up is 1 is xc1 times this factor, which actually comes from the inverse metric. Okay, so remember, I think in the previous place I actually computed what this the inverse of this metric is, and it's simply 1 over those guys on the diagonal. Okay, so then this G111 is xc1 times the inverse metric. That's the same as gamma 122, and this is the same as gamma 221. Okay, and then you simply can go and you can work out the other 6 components. Okay, so we now have these Christoffel symbols, or the connection that connects the vectors at one point, or the basis vectors at one point with the basis vectors at the other point, or the tangent field at one point with a tangent field at another point. So now let us try and do a parallel transport problem in this set of coordinates. Okay, so once again, there they are, and suppose we have this coordinate basis for our tangent space. And remember, we said we had a coordinate basis, then an orthogonal vector basis was just that, where we made sure that the inner product of these things are 1 if you dot them with themselves, and 0 if you dot them with each other. And then if we want to now, our parallel transport equation is once again dv mu dt equals to minus t mu gamma nu mu lambda v lambda. And so let's write them out. So remember, v has two components, so dv1 dt is simply t mu, so we're going to sum over mu over there, so you're going to have a t1 and a t2. So you have t1, there's 1 over there, that 1 is the same as that 1, okay, and then lambda 1 v1, okay, and so I'm basically summing over or over mu first and then over lambda. So this is minus t2 gamma 1 2, so we're summing over that 1 v1. Okay, and now I'm going to sum over this lambda as well. So we will have minus t1 gamma 1 1. Now the second component 2 minus t2 gamma 1 2. Sorry, 1 2, summing over there and summing over there. Okay, so this summation, if you find it easier to write out the sums and to make sure that you get every single component, do it. Okay, don't make mistakes by leaving things out here. All tensor expressions are explosive, but make sure you get every single component in to sum it out. There are tricks of doing this, but which only come with practice once you know how to do it. Eventually, once you've done enough examples by hand, you program it onto a computer to do it automatically. But the first couple, to get to know what's happening, you have to actually write it out. And so the trick is you do the small examples by hand, and eventually when you get 4-dimensional gravity, you tend to use a computer, except that most of the major results were derived in gravity by people that had actually learned it, because they weren't computer algebra systems available initially. Right, that only happened well after like the 1980s, and so many of the big results in GR, the analytic results, came simply by people whose minds knew how these things worked and could manipulate them and understand them. And we basically used the fundamental concepts to get answers, and also used clever coordinate systems. Okay, so that's how the first component changes. You then go in and you substitute in what we had for the Christoffel symbols, so gamma 1 1 1, gamma 1 2 1, gamma 1 2 2, and here we basically have it. It's C1 times T1 V1 T2 V2 with a minus in front, and you have a C2 times those guys. And so that's how this thing changes in this coordinate system. So that's a differential equation that connects V, that basically determines how V changes. Remember, along a curve, you know what C1 is as a function of time, and you know what C2 is as a function of time. That's given to you by the curve. Okay? And you also know what t is as a function of time, because that's the tangent to the curve. Okay, so you basically, this equation is simply a differential equation of the components of v multiplied by functions of time. Okay, you can write the same thing out for V2. The V2 component, you can do the same thing and you can write it out. So those are our differential equations for parallel transport. And now let's look at a specific example. Okay, suppose you want to go and you want to parallel transport the vector that points in the V0 vector that basically points in the ddxc1 direction, and you want to take it from point x1, x2, so your Cartesian coordinates that correspond to 1, -1 to 1, 1, and you want to transport it along a parabola. Okay, so the parabola is basically xc2 equals to some constant. Okay, and so what this basically does, it corresponds to moving from the point xc01, xc02, that, so this point corresponds to this guy, to basically the final endpoint where you have basically switched the coordinates. Okay, so we're literally going from this point to that point along a parabola, and the parabola is simply given as this value, and it corresponds to these coordinates in our transform coordinate system. Okay, and the curve that we have is simply basically this second term remains constant, okay, and this thing changes in time. Okay, so xc01 is simply that value, and xc02 is simply this value. Okay, and the moment you have the curve, you have the tangent vector, and the tangent vector is just that. Okay, and so this is also constant. So you can now see what I meant when I said the tangent vector that enters in here, as well as these coordinates, are known. Okay, so those are constants, function, and this is a function of t, and this is just a constant. Okay, so then you go and you substitute these guys in here. Okay, and you solve this differential equation with this basically initial vector. Okay, so your initial vector's components are basically xc1 and xc0. Okay, where did I get that from? I simply transformed this vector into my coordinates in terms of xc1 and xc2. Okay, so I assumed my initial vector was just simply pointing in the x or the directional derivative with respect to x. Then I took that and I projected it onto this basis in the new coordinates. And then I get the components, and I want to transport these guys using this equation. And so then I go about and I write it out. So I have dv1 dt, which is equals to that expression, okay, except that I'm now replacing, I know that only my t1 is important, my t2 is in fact 0. So that's a simplification that happened there. And I then go and I substitute in what these xc's are and what t is, and then I get this thing. So it's basically linear in t above the line, quadratic in t below the line with a whole bunch of constants. I have my v component over there and a v component over there. Okay, and I have the second equation which I want to solve is that, which is there, okay, and then you solve it. What should the answer be? You're close, but not quite. You can either solve these equations, or you can know that parallel transport doesn't depend on your coordinate system. Okay, so this coordinate system has made the fact that you are moving from here to here along a parabola look exquisitely complicated. But the fact is still, if you were to have solved the same problem in your Cartesian coordinate systems, you knew that the vector did not change. So the answer would be that the vector moves down and is still pointing in the 1, 0 direction. Okay, so a lot of the results, so this thing, and you can actually solve, you can actually integrate this thing. You can make clever combinations of V and V1 and V2 and multiply through by 1 minus 2t squared on the right hand side, and you can actually get an answer of how these components change. But whenever you transform them back into your Cartesian components, it will always be that the vector was pointing in the x direction. It basically moved along your parabola like that down to 1, and it remained pointing in the x direction. Okay, so this thing gives you a way of, and this is true only in flat space. Okay, if the space was curved, you would actually have to solve these exactly, or you would have to try and find another shortcut. But just from the perspective of finding the equations you must solve, this is the mechanics that you go through. From the perspective of finding the actual answer, you either put these equations on a computer and then you should get the right answer. In fact, that's often how I test codes, is I take a problem where I know the answer in a simple coordinate system, then work in the coordinate system I want to work with in general, and then test it by actually giving the equation and asking them to solve it. Because these equations you can just solve like with the Python code that you guys are familiar with that I gave you for the Strogatz course. I mean, that's literally what they are. You have a set of non-autonomous equations that you can just specify the right and size for and then solve it on the computer, and it'll actually draw you the line. Or rather, you can actually plot the solution, which will give you the line, and you can plot your vector components, and you'll see how it's parallel transported. But in this particular case, because in the Cartesian coordinates, basically any vector doesn't change, it'll just move down. Your answer over here at the end, when you get it, is you'll simply get whatever components you have here, transform them into Cartesian components, and then you'll find that it is once again just this vector that hasn't moved, or that has just moved down. Okay, but these are the equations for doing it in a coordinate system. And when we work in curved space, like with GR, these, or like when we transport a spin vector in GR, we are actually working with these things. And then there's a lot of people that have done a lot of hard work in finding elegant answers. And that is why when you have this orthogonal rotator in for 0737, and you parallel transport its spin vector along the orbit, those are the equations that are computed that actually says it'll come back and be, the orthogonal rotator won't precess. Okay, I'm literally solving these equations for every possible orientation, and I'm observing that the one orientation actually doesn't change when you go on. And that's understood.
Very smart.
Very smart. So I did actually work out the answer. So there's an analytic answer for these equations. You can try and see if you can see how I got it. Okay. And so this is how the components change along with time as you move along, as you transport it. So the components are changing with time. But if at every point along the curve you take these components and you transform them back to Cartesian components, you will actually just get that it points in the x direction. Okay, so if you want to actually go through the exercise, and I'd advise you to do it because being able to solve these things in a fit way is not a bad plan. This is the answer you'll get, so it does exist. And then you can just verify that it in fact gives you back a vector that just points in this direction at every single point. Okay. And once you've done that and sort of understood every step I've done here, I think you pretty much have mastered the, or at least have a clear picture. If you can do the practical example using the definitions that we've collected along the way, then you can basically at least write down the equations for parallel transport and know what a covariant derivative is. And if ever you want to delve deeper, you can go back and at least see. It's only when you actually start solving more complicated things that you need to go back into the machinery of how the metric was constructed, or how the connection was constructed, how the metric was constructed. For the first trial equations that you work with, you can just basically use the mechanics in the last two slides. In other words, get your connection in, given the metric, work out its inverse, work out its derivatives, and then combine it to get the components of the Christoffel symbols, and then know that this is your parallel transport equation. Okay. Just one comment of what we're going to do in the future, your geodesic equations. If you parallel transport a vector along itself, in other words, if you change this v to actually t of mu, okay, what you then have is a second derivative for the coordinates of your path is equals to a quadratic term in the first derivatives. Then you have a second order system that you can always prove is equivalent to the geodesic equations you've been working with. Okay, so a geodesic equation is a vector that are the unique paths that parallel transport themselves, the tangent vector along those paths. But I'll get back to that next time. So the moment we've got this parallel transport, we've basically got our geodesic equations as well that you've been using. But you at least now understand why I took the other means of introducing it the first time, because I didn't have basically a course to develop it for you before you could start playing with them. But the ideas that the geodesic equations are intimately connected with your metric and with your manifold, and with a parallel transport. There are very few equations that actually happen on manifolds, and the geodesic equations and the curves that result are basically the most fundamental ones. Or I like to think there are people that will differ with that, but they are a very fundamental entity in any manifold. Right, and that's it from me. Any other questions?
Just there at where you have your initial point, your end point, and then just below it, are